Hi, I'll be doing question 53 today, which states, one day when you come into physics lab, you find several plastic hemispheres floating like boats in a tank of fresh water. Each lab group is challenged to determine the heaviest rock that can be placed in the bottom of a plastic boat without sinking it. You get one try. Sinking the boat gets you no points, and the maximum number of points goes to the group that can place the heaviest rock without sinking it. You begin by measuring one of the hemispheres, finding that it has a mass of 21 grams and a diameter of 8 centimeters. What is the mass of the heaviest rock that, in perfectly still water, won't sink the plastic boat? So essentially the importance of this question, and the reason why we're finding this, is we're trying to understand that relationship between a mass of an object that is floating in water and the force of buoyancy acting upon it, and how mass and buoyancy kind of work together in a way to keep an object afloat. So, right off the bat, a hemisphere is essentially just half of a sphere. So that makes our hemisphere volume very easy to find, because essentially it's just the volume of a sphere divided by 2. And I found that to be 134.04 centimeters cubed by just plugging in the radius, which we had gotten from the diameter over here. Next, I remembered from lab last week that all objects that are afloat kind of have this relationship between the force of buoyancy and the force of gravity on it, and they're equal. So, if you look over here, I drew this just little visualization of how these two forces, the force of gravity on this object and the force of buoyancy on this object, are kind of working against each other to keep this object afloat, and they're also equal. So, expanded, the force of buoyancy is the density of the fluid times gravity times the volume displaced, equal to the force of gravity on the object, which is just the mass of the object times gravity. So immediately I wanted to isolate the volume displaced, because I thought, well, we're trying to keep this boat afloat, and essentially if we displace the amount of the exact amount of the boat, that would immediately mean that this boat is completely submerged and it would sink. So we don't want that, hence why I put this less than symbol here, is because we want that volume displaced to be less than the volume of our whole boat. Maybe we still want just this little lip of the boat to still be above water to prove that it is still floating. Now, I also augmented the mass of the object and added this plus r. This plus r is essentially just adding the mass of the rock. So r is the mass of the rock that we're trying to find. The reason why I added them together is because these two masses are working together to act against this buoyancy force. So together they are essentially making up the mass of this whole object. Now, when I multiplied the density of the fluid on each side, I found that it just equals 134.04 grams. That's because the density of our fluid in this case is just water. It's nice. It's just 1 gram per centimeter cube. Now, then I isolated the mass of the rock that we were trying to find and found that it has to be less than 113.04 grams in order for the volume displaced to not surpass the volume of our whole hemisphere, our whole boat. Remember, we want to keep this boat afloat, and we don't want to submerge the whole volume of this hemisphere. Now, now that we know what the volume of our rock should not essentially be, so it should stay just under this, so it could be like 112 grams and still float. I'm going to move on to what tricky concepts could have been overlooked in this question, and that's, say this box is like a little tub of water. If an object is kind of just floating in the middle, like it's not touching the bottom but it's not touching the top, that's still considered floating. So therefore this equation could be taken in that way, which we would not want, which is hence why I also set it less than this volume displaced, because this would immediately just assume that our entire boat is not underwater, and therefore this situation would not happen.